dimensional trace reversed metric. But if I ignore the slight complication for the moment, let me look at these two equations over here. This first equation, capital M and capital N, still break up into mu nu, mu y, and yy. There's three equations hiding inside here, the mu nu equation, mu y, and yy equation. They all look the same, so I was lazy and wrote them as one. But if I took the mu nu equation here, the space-time equation here, box h bar mu nu equals 0, d mu h bar mu nu equals 0, that is just a four-dimensional linearized Einstein equation in harmonic gauge with one subtlety. If I look at the mu y index over here, this is box h bar mu y equals 0, d mu h bar mu y equals 0. That should look like a Maxwell equation or a vector field equation in Lorentz gauge. And then I also have box h bar yy equals 0 without any additional transversality conditions, because h bar yy doesn't carry a space-time index. Let me actually break that apart for you. H, capital M, capital N, the five-dimensional metric, I'll write in terms of four-dimensional fields. The space-time part of it, I write it as h mu nu. The yy component, I write as 2 phi. 2 is just a matter of convenience. I don't really need the number 2. But I'll just include that over here. It's just a matter of definition. And off-diagonal components, the h mu y components, since it's going to look like a vector field, I'll just call it a mu, which we'll refer to as the graviphoton, the photon that comes from gravity. As I said, there's a slight complication in which the five-dimensional trace reversal gives you something like that. That's because phi over here is part of the five-dimensional trace. The space-time part of the trace reverse h, this h mu nu minus 1/2 eta mu nu h rho rho is the four-dimensional trace reverse h. There's a dilaton phi, well, there's a scalar phi left over here. And then the phi 5 component is a little bit different like that as well. However, when you do that, you can end up with basically the Laplacian equation for phi, a mu, and h bar mu nu. Box phi equals 0. That's a massless Klein-Gordon field. So it's a massless scalar. Phi is a real scalar. This is a massless real scalar. I have box a mu equals 0 with a Lorentz gauge condition, d mu a mu equals 0. So a mu is basically a Maxwell field, or a massless U1 field. You might wonder, why did this Lorentz gauge condition come out over here? Who decided that the Maxwell field had to be a Lorentz gauge? The answer to that, of course, is I already started with harmonic gauge in 5 dimensions. I made a choice of gauge for my 5-dimensional Einstein theory, and that shows up in this Lorentz gauge condition over here. The 4 dimensions, I got box h mu nu equals 0, and then the harmonic gauge condition in 4 dimensions is a little bit different because I have a right-hand side d mu phi because of this mixing term over here. The ordinary 4-dimensional Einstein theory in harmonic gauge would not have this right-hand side over here. So there's a bit of a mixing of the dilaton or the scalar with the metric field. Turns out that this mixing can be removed. I can shift my 4-dimensional h mu nu over here into h mu nu half by removing a dilaton component, or removing a bit of the trace component like that. Once I make this shift over here, I end up with standard 4-dimensional linearized Einstein's equations in harmonic gauge. I'll come back to this shift a little bit, because it goes to show a little bit of the complications in these Kaluza-Klein reductions, that I don't always get the standard basis in lower dimensions. I might end up, and usually what happens is you end up with dilaton or scalar field shifts in the various places. So I'll come back to the zero mode reduction, but let me jump to the massive case as well. So now if I turn to the case n not equals to 0, these are the massive Kaluza-Klein states. Then if I go look at the 5-dimensional harmonic gauge condition over here, this is the case where I can divide by mass, and I can solve for an off-diagonal component. Hy nu can be written in terms of a divergence of h bar mu nu. HYY can be written in terms of the double divergence of H bar mu nu, like that. What that means is if I solve for a massive KT state, if I solve the equation of motion, which is a massive box minus m squared equation, if I solve for H bar mu nu over here, then the additional components of the metric are determined just through these two equations over here. So H bar mu nu is the only independent part of the metric. And this corresponds to a massive spin 2 field, at least at the linearized level. And so in the massive Kaluza-Klein tower, all I find is a massive, at every level n, there's one massive spin 2 field with mass n over r. There's no spin 1, there's no spin 0. Turns out there's another way to understand that a little bit, which is, I started out with a massless theory in 5 dimensions. So whatever modes I would have expanded in 5 dimensions, at some sort of hand-waving or superficial level, everything should have been massless. Now, in order to get massive spin 2, I can do something like a Higgs-type mechanism, or a bit of a generalized Higgs mechanism. I can take a massless spin 2 particle, it can eat the spin 1 particle to get the helicity plus minus 1 states, and then eat the spin 0 particle to get the sort of helicity 0 state as well. So I can think about this massive spin 2 as taking the spin 2, spin 1, and spin 0, the h mu nu, h mu y, and h y y components, and eating them all to form just one physical massive spin 2 at each level and in the Kaluza-Klein tower. So I don't have a good table, but the summary over here is when I reduce 5-dimensional gravity in a circle, I end up with 4-dimensional gravity, 4-dimensional U1 field, and a 4-dimensional scalar, Einstein-Maxwell dilaton gravity, along with an infinite tower of massive spin 2 fields. So it's a zero-mode sector, Einstein-Maxwell dilaton. These are massless fields in 4 dimensions, coupled to a massive Kaluza-Klein tower. And as I said before, we can do a truncation. I can remove the Kaluza-Klein tower, leaving only Einstein-Maxwell dilaton. And in fact, sometimes when we talk about Kaluza-Klein reduction in a circle, we imagine that the tower has been truncated away for us. So one of the original thoughts, of course, was if I shrink the circle to 0 size, and it's sort of a true compactification idea, I make the circle so small you can't ever see it, then the masses of the Kaluza-Klein tower are given by sort of 1 over r factors. So the masses of the Kaluza-Klein states get heavier and heavier and heavier as I shrink the circle to smaller and smaller sizes. Eventually, I take the limit as the radius goes to 0. The Kaluza-Klein tower goes off to infinity. I ignore that. I'm left with Einstein-Maxwell dilaton as the sort of the zero-mode sector that survives. Yes?
I'm concerned about the symmetry of the theory. So originally, there is a diffeomorphism in the dimensions.
Right.
After compactification, of course, you have diffeomorphism in 4 dimensions. Maybe there are more symmetries after compactification. Or some of the dimensional...
Well, a rough picture, which may not be perfect, is 5-dimensional diffeomorphisms. I can break up into a 4-dimensional part plus a 5th-dimensional diffeomorphism. And the 5th-dimensional diffeomorphism is basically reparameterization along the circle direction. And that ends up being the gauge freedom in the gauge field over here. Although there may be issues about, global issues of periodicity or something like that. I'm just thinking from a local point of view.
So 5-dimensional diffeomorphism is sort of broken by compactification, or it's not broken?
Locally, I don't think it's broken, but
so
well, there's a notion. What do you mean by 5-dimensional diffeomorphisms? Reparameterization of y. That. Well, I restrict myself to 0 modes, which is the 0-mode sector over here. Then I more or less removed y, and so that's sort of a subset of 5-dimensional diffeomorphism. So it's not the full thing. I think that's correct. All right, well, this is sort of a snapshot of the original Kaluza-Klein idea of reducing five-dimensional gravity to four-dimensional gravity plus U1 field plus a scalar field. Now, the original idea of Kaluza, I think, did not include the scalar field. He just thought the fifth-dimensional circle has a fixed radius, GYY equals 1, or some constant number. It turns out it's actually inconsistent to truncate the scalar field away. So it was pointed out not too long afterwards that you really do need to include the scalar field for consistency. Basically, because the Maxwell field will source the dilettante. And so once they have a source for the dilettante, you can't just set the scalar field equals constant. Well, let me go back to the, oh, sorry.
Why do you say it's inconsistent to do that? Can I just consider that as fixing gauge?
The scalar field phi?
No. I'm just saying, can I just consider this as fixing gauge? What GYY equals to 1?
Oh, GYY equals.
Right. I mean, I would expect that the scalar model would be hidden somewhere in the G mu nu.
Yeah,
case.
no, you're absolutely right. I can fix a gauge GYY equals 1, but the scalar shows up somewhere else.
Okay.
But the point is, the physical scalar, or physical spin zero field cannot be
Always there.
truncated, it's always be there, because it will be sourced by the Maxwell field, for example. But you're absolutely right, in terms of GYY equals 1, that is a gauge choice. Oh, so let me look a little bit more at the zero mode sector. I showed you how to do a linearized Kaluza-Klein reduction just by doing the linearized Einstein equation. But we can do a little bit better when the Kaluza-Klein tower is a little bit complicated. If I focus on the zero modes, I can do a little bit better by trying to make a full nonlinear reduction. Let me just remind you, the linearized choice was the linearized HMN fluctuations with something like that. This can motivate me to write down the full nonlinear onsets. So let's solve the five-dimensional Einstein equation exactly. And if you do that, but I decide to write down a line element over here, which is equivalent to the components of the metric G capital MN, like that. Obviously, H mu nu should be part of a G mu nu, like that. This 2 phi thing, this is a GYY component. The GYY component, if I just call it e to the 2 phi, the linearized expansion is 1 plus 2 phi. The 1 is the background metric, the 2 phi is the fluctuation field like that, so the 2 phi is represented by e to the 2 phi. Now for convenience, it's natural, if I ignore the gauge field A mu for the moment, G mu nu dx mu dx nu plus e to the 2 phi dy squared is exactly what I would have said for G mu nu over here, e to the 2 phi over there. Once I write down a five-dimensional metric like that, there's a natural way to turn on the off-diagonal components, which is to say, if y is a circle, and I wanted to consider modes that are symmetries on a circle, then I can shift dy I can shift y by a constant. But instead of shifting y by a constant, I can actually gauge that symmetry by turning on a sort of a shift symmetry over here, a mu dx mu, like that. And it's just a very natural way to introduce an off-diagonal metric component. And when I write out the components, it looks like that. Now, at the linearized level, a squared here I ignore. E to the 2 phi times a mu. At the linearized level, a, if I think of it as a fluctuation, e to the 2 phi I just set equal to 1, gives me exactly that at the linearized level. So this is sort of a nonlinear generalization of the linearized fluctuations like that, put together in a convenient sort of manner. Another nice thing about writing the metric like that is I can go into a Vielbein basis. For my four-dimensional metric over here, I can introduce four-dimensional Vielbeins. And the fifth dimension, I guess when I was typing this up, I decided to call it the ninth dimension, but you can think about it as the fifth dimension. It's the extra dimension. I can think about the Vielbeins, basically a square root of the metric is just something like that. This allows me to compute the Ricci tensor. So remember, the vacuum Einstein equation is just Ricci tensor R capital Mn equals 0. In order to solve the five-dimensional Einstein equation, I want to write down the five-dimensional Ricci tensor in terms of my four-dimensional fields. So it's a nice exercise. It's a nice homework exercise, which the first time I did it, it probably took me like a week or something. It was rather tedious, but once you've learned the tricks of doing it, it's not too bad. The five-dimensional Ricci tensor, using the metric decomposition, I can break up into four-dimensional components. And the reason I introduced the Vielbein is for convenience. I wrote down Vielbein or flat space components of the Ricci tensor like that. AB is the space-time part, A9 is the off-diagonal part, and 9 is like the YY component of the Ricci tensor. Now, whenever you do sort of Kaluza-Klein reductions with gravity, things can get very confusing. This is the five-dimensional Ricci tensor calculated from the five-dimensional metric. I'll put down the little d over here, that's my lower dimensions. This is the four-dimensional Ricci tensor calculated from the four-dimensional metric. Then these are all the additional things associated with it. These covariant derivatives are computed with the four-dimensional Christoffels, computed with the four-dimensional metric, and so on. There's a bit of a pattern to this. The vacuum Einstein equations is to set these Ricci tensor components equal to 0. So let me start with the middle one, because it's probably the most obvious one to see. If I want to solve this equation over here, I can ignore these prefactors. This is a covariant derivative, nabla b, of this e to the 3 phi FBA. This is basically the Maxwell equation. This is a four-dimensional Maxwell equation, except that it has this e to the 3 phi component over here. This Maxwell equation can be obtained from a Lagrangian, which is basically 1/4 of mu nu squared, except that to keep this e to the 3 phi factor as well. So if you think about deriving an equation of motion from this Lagrangian, just focus on the second term over here. This Maxwell term has this equation of motion. Now let me look at the 9,9 component, or 5,5 component. Let me ignore the d phi squared right now. If I ignore that, this is box phi, this is Maxwell-like equation. This is a Klein-Gordon-like equation. This is a Klein-Gordon equation for phi, and it's sourced by f squared. So the Lagrangian is going to look very funny over here, because it's this term as well. But roughly speaking, this is a scalar field equation, which has a source f squared for the scalar field. This is what it's going back to on the consistency idea. If I have the Maxwell field f squared over here, it serves as a source for phi. I cannot set phi equals constant. If I set phi equals constant, first two terms are gone, then I get f mu nu squared equals 0. Well, there's a solution to that. It's just f equals 0 basically, or something like that. That's not the solution I'm looking for. So this is a Klein-Gordon equation with f mu nu squared as a source for my scalar field. Now let me go back to the space-time components of Ricci over here. This is the four-dimensional Ricci. So this is corresponding to the four-dimensional Einstein tensor. Well, if I calculated the Ricci scalar, and I could form an Einstein tensor out of that, this is basically giving me a four-dimensional Einstein equation, where the d phi squared, the nabla phi, and the f squared, this is the stress energy tensor. This is basically the four-dimensional stress energy tensor. And this is the four-dimensional Ricci tensor. So, out of nothing in 5 dimensions, well, out of gravity in 5 dimensions, no stress tensor in 5 dimensions, I now have a four-dimensional stress tensor over here. Four-dimensional stress tensor is scalar field and Maxwell field. And so the Klein-Gordon picture over here, sorry, the Kaluza-Klein picture over here is the space-time component of Ricci. Gives me my four-dimensional Einstein equation. Off-diagonal term over here gives me the four-dimensional Maxwell equation, and the YY equation gives me the scalar equation. Now there is a bit of a complication. If you think about a scalar field stress energy tensor, scalar field stress energy tensor doesn't have this nabla phi term. So in fact, if you work at it a little bit, you'll realize that these three equations of motion are not sort of the standard Einstein-Maxwell-Dilettante equations of motion. However, they can actually be derived from this four-dimensional Lagrangian over here, which looks kind of funny. This is not canonical Einstein-Hilbert because this is e to the 2 phi in front of it. This is more of a, sometimes it's called a Brans-Dicke term. The Maxwell term over here, I already explained, gives rise to this equation of motion. That's very simple. E to the 3 phi is just e to the 3 phi. That basically is what it is. Now, normally a scalar field should have a kinetic term, d phi squared. This is not a typo. As far as I know, it's not a typo. There's no d phi squared. Oh, there might be other mistake, but no d phi squared is done on purpose because these equations are derived as given over here without the d phi squared. This is not to say that phi is trivial, because if I derive the Einstein equation from here, this is the Brans-Dicke type thing. So if I vary this equation with respect to g mu nu to get the Einstein equation from an action principle, the variation of r gives you something, or the variation of square root gr gives you something like the Einstein tensor. But when you do that standard derivation, you actually drop sort of an integration by parts term, or you drop the total derivative term. The term that you drop to normally get the Einstein tensor out of the Einstein-Hilbert action depended on dropping the total derivative term. That total derivative term is no longer a total derivative when I have an e to the phi over here. So that gives me this type of term, like that. So this is a very unusual action. In terms of this sort of dimensional reduction gain, people usually talk about various so-called frames, which is from a string theory point of view. If I call phi the dilaton over here, a so-called string frame action usually has an overall factor e to 2 phi times some stuff inside here. This is not the string frame because I can't pull out an overall factor. The number 2, I can always normalize away, but this is e to the phi, this is e to the 3 phi. I cannot factor that out to a common factor of e to the phi times a rest of the action. It's not the Einstein frame in the sense that it's not an Einstein-Hilbert action, because that's e to the phi out front. However, since I invented, well, not me, but since I wrote down the Kaluza-Klein ansatz, I decided that the 5-dimensional g mu nu should go into something like a 4-dimensional g mu nu. I could have made a different choice. I could do what's called a Weil rescaling. What I call g mu nu in my reduction ansatz could be rescaled by a Weil factor e to the 2 rho g mu nu. Rho can be x mu dependent. So it's a space-time dependent rescaling of the metric, or Weil scaling. When you do that, the Ricci tensor gets rescaled in a slightly obnoxious way, which is dimension dependent. If I give myself the choice of Weil rescaling, what I can do is if I rescale by phi, there's another exercise for you to try, is if you rescale by phi, put in the numbers over here, the action I gave you on the previous slide. If I take this action, rescale the metric by e to the 2 phi, then I get something like that. This is what I call the string frame metric. There's an overall exponential factor of the dilaton over here times Einstein-Hilbert r, something d phi squared minus 1/4 f mu nu squared, like that. This r over here, minus 1/4 f mu nu squared, looks very conventional. It does have a dilaton factor out front. This thing over here is dimension dependent. I don't care about that. I can canonically normalize phi by rescaling phi. But in my metric conventions, which I guess I forgot to mention, minus, plus, 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 mostly plus metric over here, the standard kinetic term should have a minus sign over here. This looks like it's the wrong sign kinetic term for d phi squared. That's because the string frame has some additional dilaton factors over here. The other frame people like to do is to rescale, so remove the Brans-Dicke field in front of R and make it as a separate scalar. So I choose phi. So to choose my Weil scaling in a slightly more, different way like that, I can rescale out. I can remove e to the phi in front of the Einstein-Hilbert term, and end up with what's called the Einstein frame Lagrangian, like that. Einstein Hilbert action. D phi squared with the correct sign kinetic energy term. This can be normalized away if I wanted to. And then minus 1 part F mu squared with the dilettante coupling, like that. So this is something that's called Einstein Maxwell dilettante. Now, if you've been paying attention, you realize that this shift over here is exactly the shift I did in the linearized analysis to sort of decouple the metric from the scalar field. It's not a mystery. It has to be the same. So I spent a little bit of time talking about Kaluza-Klein gravity, reducing the five-dimensional gravity theory to give you Einstein-Maxwell dilettante in 4 dimensions. Of course, what I really want to do is to consider the supergravity case. And part of the complication of supergravity is to have additional fields. I have supersymmetry and I have fermions to deal with. If I ignore supersymmetry and fermions for the moment, then what I showed you at the end of yesterday was that I had 11-dimensional supergravity. I can reduce that on a circle to d equals 10. This is just a summary of what I mentioned yesterday without going into the details. Is in addition to the 11-dimensional metric, I also had a 3-form potential, A, M, N, P, something like that. If I reduce that on a circle, I can make all these space-time indices, mu nu rho, or space-time mu nu times the 11-dimensional index. Since I have one circle, I cannot antisymmetrize more than one circle dimension, so that's all I have, something like that. I can write that in a form notation. For a 3-form potential, decomposes into a 3-form potential in 10 dimensions, plus a 2-form potential, A mu nu 11 over here, wedged into dy. That's my 11th dimension coordinate, like that. Now, if I did that, I can compute the field strength. dA3 gives me the 4-form field strength, and it's very easy. dy is closed, so I just hit dc and db like that. Now, there's a bit of an interplay between the 3-form potential and the metric reduction. The 11-dimensional metric reduction, I will turn on an off-diagonal metric component, which is the ground photon, which means if I wanted to rewrite this in my natural Vielbein basis, dy is associated with my shift symmetry. So the gauge shift symmetry is really dy plus A. So there is some nice way of writing the additional dimension in terms of the Vielbein as dy plus A. There's a dilettante factor, which I ignored in this equation over here. But if I want to write dy as dy plus A with the gauged shift symmetry over here, I've added an extra term here. I can't just add A to dy over here without subtracting it off, which I did over here. And so this equal sign is just an identity, but it's a reorganization that says in 10 dimensions, the natural 4-form is a shifted 4-form, which I call F4 tilde over here, and the 3-form is, as it is, H equals dB. And as a string theorist, H equals dB is the familiar NS-NSB field over here. So this is just a quick snapshot that when you turn on the graviphoton or off-diagonal metric components in these Kaluza-Klein reductions, often you end up with all these shifted field strengths in these supergravity reductions. So I'll just pause a moment here and ask if there's any questions, and then I'll jump into supersymmetry analysis a little bit. Good, everyone wants to see supersymmetry. So when I talk about circle reductions, or more generally, reducing on the torus, I'm reducing on the flat internal manifold, and it turns out I don't break any supersymmetries. So I started with 11-dimensional supergravity, 32 real supercharges. I keep on reducing circle, circle, circle. I can get to all these lower dimensional theories with 32 supercharges. However, there's something else I can do. I can pick more complicated internal manifolds that's not a torus. And by picking more complicated manifolds, I can break supersymmetries. Usually I don't want to break